All right, I'm going to refresh your memory on reduction here. Suppose we have two languages, L1 and L2 over the alphabet, sigma 1 and sigma 2. And then a reduction of L1 to L2, we write that this way, is a function R from strings to strings. All strings over sigma 1 to all strings over sigma 2, which has a property that if W is any string over sigma 1, then W is a member of the language L1 if and only if R of W is a member of the language L2. And we write that this way. Now, why is this a reduction in the sense that you've heard the word reduction, like somebody says, I solved this problem by reducing it to that problem? Well, if you look at this, if I want to know whether W is a member of the language L1, and if I can compute the reduction, then all I have to do is decide whether the reduced string is a member of L2. And that's one of the reasons it's useful. Cut. All right, now, there are many NP-complete problems known. There's a list on Wikipedia on a website, and other websites, but it only is incomplete because there are thousands of NP-complete problems known. And of course, I think theoretically there are infinitely many of those. Now, I'm only going to hold you responsible for a certain subset of them, and that includes these. I mean, knowing that they're NP-complete. Now, SAT is the granddaddy problem. It's like the zero patient in coronavirus or something, because this is proved to be NP-complete from first principles. And that means it doesn't depend on anything else being NP-complete. All other NP-complete problems can be derived from it by reduction, as in the previous few minutes, earlier in this video. This particular problem is called 3CNF SAT, which I haven't described. Subset sum means that you give a number and then you give a sequence of numbers here, and given that sequence of numbers, we ask, is there a subset of these numbers that adds up to this total? And in this particular case, I can see that there isn't any subset that adds up to 14. So the answer for this instance is no. The knapsack problem, we can say that the thief is going into, say, King Tut's tomb with a knapsack that holds 50 pounds. And he's trying to walk off with as much treasure as he can but he has to make sure he can carry it, so it can't be more than 50 pounds. Now that's not a decision problem, so the way to make it a decision problem is to say, can the thief find $1 million worth of stuff and still fit it into his knapsack? Then it's a decision problem. Now the traveling salesman problem is also NP-complete. And for example, if we had a graph here, and we had a bunch of cities here, and a bunch of weights here, and our question is, what's the cheapest way to visit all the cities in a Hamiltonian cycle where each road costs a certain amount? This road costs 0 and so forth. And so, for example, in this particular case, the cheapest way to visit all of them would be that Hamiltonian path there. You might say, how do I know? Well, because it's very simple. But in general, it's quite difficult. It is, in fact, an NP-complete problem to decide whether a given path is the best possible. But we make that into a decision problem by saying that the traveling salesman has a certain budget. And the question is, can he travel to all the cities in the Hamiltonian path without exhausting his budget. All right, so cut. Here I'm explaining the Boolean satisfiability problem. I'll use this notation for and, for not, and for or. Now this particular expression here, P and not P, is a contradiction because it's impossible for it to be true regardless of the truth value of P. And this particular one is a tautology, meaning no matter what the truth value of P is, it's true. Now this particular thing is satisfiable, meaning there is a way to assign truth values so that it's true. Now the tautology is also satisfiable because there's an assignment that makes it true. But the opposite of a contradiction is satisfiable. Now most people would say the opposite of a contradiction is a tautology, but that is not true in the way we're looking at things. So when we have a Boolean expression here, let's say this Boolean expression is called E for expression, and these are Boolean variables. X1, X2, and X3 are Boolean variables. The question is this expression satisfiable? Which is the same as saying, is it not a contradiction? Well, it turns out this one is satisfiable. I can make an assignment as follows. X1 is false. X2 is true. And X3 is true. Now, with that assignment, this expression is true.
Mm-hmm.
Therefore, it's not a contradiction, or in other words, it's satisfiable. So the SAT, as it's abbreviated, is the following problem. Given a Boolean expression of a certain length, whatever the length is, does there exist an assignment to all the Boolean variables such that it becomes true? Now, a Boolean variable could appear more than once in the expression, and it has to have the same truth value. So if I say that x2 is true here, it has to be true there. And so it's relatively simple. I could run into a contradiction where it might not be so obvious. But it turns out this problem is NP complete. One way you could solve it is to try all possible assignments and see if one works. How much time would that take? Answer: the number of possible assignments is an exponential function of the length of the string, and therefore it would take exponential time, although it would only take polynomial space because you'd only have to keep track of how far you've gone so far. This problem was proved by Karp and Cook to be NP complete from first principles, not depending on any other NP complete problems. Cut. Well, now, initially in the first paper, Richard Karp and his co-authors proved that for any NP language L, there is a polynomial time reduction of L to SAT, Boolean satisfiability. This is then, by definition, proves that SAT is NP complete. Now, for each L in the big list, he published a big list of NP complete problems. For each one of those L's, he proved that SAT reduces in polynomial time to L. It looks backwards, and it's difficult. And the kind of question I like to ask is the answer is based on whether you get these confused. Cut. All right, the independent set problem is one that I'll expect you to know, and that's as follows. Does there exist an independent set of size k in a given graph G? All right, so we're given an undirected graph G, vertices V and edges E, and we're given an integer k, and we ask, does there exist a set I of vertices? Now that's the independent set, such that I has size k, there are k vertices, and no two vertices, no two members of this set I have an edge in common. This problem is NP complete. Cut. For example, if G is this graph here, which has 6 vertices, if we let K equal 3, then there is an independent set of size 3. There is? Yes. This particular set here has is independent, and there are 3 vertices in there. However, if K is 4, then the answer is no.